Welcome to the Journey in Silicon Innovation at AWS. My name is Ali Saidi. I'm a senior principal engineer and the lead engineer for our Graviton-based instances. I'm delighted to be here today to talk to you about the custom chips we're building in AWS. So far, we've built chips that span areas including I/O and data center infrastructure, core compute, and machine learning. With the Nitro system, we moved functionality away from the traditional hypervisor. That's the piece of software that takes a big machine and turns it into multiple virtual machines. Onto purpose-built chips. Then this improves I/O performance, frees up host CPU cycles, and raises the bar on security in our servers. Then with Graviton, we've built a host CPU that delivers the best performance and price performance for a wide range of workloads in EC2. And lastly, with Inferentia and Trainium, these are purpose-built deep learning accelerators, one for inference and the other for training, that provide best-in-class performance and price performance. I'm going to talk about each of these in turn over the next 45 minutes or an hour. But first, I'm going to spend a little of time about why we're going through the process of building chips in AWS. And the answer here is really simple. We're building chips where we can lead to direct customer value. One of the ways we do this is to specialize the hardware for the use cases we have in AWS and the scale of AWS. So I'm going to show you how we've tailored the Nitro system to AWS infrastructure to both improve performance and the security of our servers. The second is we get better speed of execution by owning the end-to-end development process. We get to decide when a development is going to start, when we're going to deliver it to the customers, and the various steps and milestones in between. This allows us to shrink the time from concept to deployment by putting the teams building the hardware and the software together in a room from the start of the project so that we can get the code and the firmware running on the hardware before we have even made the chip yet. And we get to leverage our own AWS resources to scale up our compute needs as we get towards the end of the project and speed up that time to delivery. Building our own chips also lets us innovate more and then therefore create more value. Because when you have the team developing the hardware, the firmware, the software, the systems, the servers, all under one roof, you don't have the traditional silos you might have. And by removing those silos, people can innovate across boundaries where they typically couldn't. That means we can focus more on customer use cases and not on artificial abstraction layers. And lastly is security. Nitro provides us a mechanism to enhance the security of our servers through a hardware root of trust, verification of firmware on the server, and limiting interactions with that host to a narrow, authenticated, and audible API. Nitro is a fundamental rethink about how virtualization should be done in the cloud. And it all started with a simple question. After building EC2, if we applied all our learnings, how do we change our servers? And we got a lot of good suggestions. One was improved throughput and performance. Some were simplifying the hypervisor to allow more workloads to run on EC2, reducing latency and jitter, or even having our bare metal instance types, where you get all the features you'd find in an EC2 instance, but you can do that running your own hypervisor if you wish. On the security side, we had ideas like transparent encryption for all I/O without a performance hit, a hardware root of trust, limiting operator access and removing the ability for people to log into servers, for example, and having a narrow audible API. And Nitro gave us a path to do all of this. Nitro is a combination of purpose-built hardware and firmware. And we're on our 5th generation now of these custom chips. We introduced Nitro back in 2017 with a C5 instance. But we really had started working on Nitro in 2013 with a CMP3 instance when we announced enhanced networking. We had higher performance networking, we had lower latency, we improved CPU utilization. And over time, we expanded this idea of moving functionality out of the hypervisor on special purpose hardware to other types of I/O. Eventually, we'd offloaded that hypervisor so much that we got to change it, and we built the Nitro hypervisor. Nitro instances are now powering over 400 instance types in EC2, and every instance type we've released since 2017. So if you've used any of our 5th generation or 6th generation instances, you've been using the Nitro system. This is how a server looked before the Nitro system. We have the customer instances, and they're running on top of a hypervisor called Zen. Zen's great, but it also did a lot. It did memory management, it did CPU scheduling, did device emulation, limiters, security groups, and quite a few other things. It even had a full-blown Linux user space in this privileged DOM0. All this functionality used resources on the host CPU. So we started offloading these capabilities to hardware devices. So we have our Nitro cards that do this. It's not just one card, but it's a family of them with different generations of Nitro chips that offload functionality like the VPC network on EBS, the Nitro SSDs, and system control functionality. I only have time to talk about a couple of these today, so I'm going to start with the first one we did, which is the VPC networking card, and also one of our latest announcements, the Nitro SSDs. With the Nitro card for VPC, we offloaded some of these I/O functions, like packet encapsulation and de-encapsulation, security groups, flow log, routing decisions, and more. With our newer versions of the card, we have transparent 256-bit AES encryption of all the data in transit with no performance overhead. The VPC card presents an ENA device, and this is the way you've interacted with it through an elastic network adapter device and the driver that goes with that. And one of the coolest things about ENA is it's been extensible. When we originally announced ENA, we had 10 gigabit networking. We went from 25 and to 100, and we're not done yet. All of this without changing our ENA driver. So you could take or a machine image, you could stop it, you could start it on a machine with more network bandwidth and just realize that without having to change your drivers or anything else. And that's pretty unique. The other thing we enabled with the Nitro card for VPC is the elastic fabric adapter. EFA has network features that are geared to HPC and machine learning workloads, because these workloads are a bit unique. They need both low latency and high bandwidth. Most workloads need one or the other. They either need low latency and bandwidth isn't very important, or they need high bandwidth and latency isn't very important. But these ML and HPC workloads need both. So we built a kernel bypass networking stack here and used another AWS developed technology called the Scalable Reliable Datagram, or SRD, to be able to load balance traffic across many paths to our network, reduce fabric congestion, and hotspots within it. Now let's talk a bit about the Nitro SSDs. And before I dive in here, I've got to tell you a little bit about how an SSD works. And there are really two interesting components on this SSD. The first is the NAND. That's where the physical bits are stored. But it also has a lot of peculiarities. The biggest one is you can only write to that device after the NAND has been erased. But the erasing process doesn't operate on bytes or even small blocks. It tends to operate on megabytes. And so even if you want to just modify one byte in a file, you end up having to copy a lot of that data to a new location and eventually go off and garbage collect old written locations. There's a second chip on this called the FTL, or Flash Translation Layer, that does this behind the scenes. It maps logical addresses to physical addresses. It performs this garbage collection and manages where leveling across all the NAND. But ultimately, it does something that looks a lot more like a database than you might expect with write-ahead logging. Now, this is fine, but every flash manufacturer produces their own SSDs with their own FTLs. And on the average case, they all do a good job, but they all have different peculiarities, just like different databases might have different performance characteristics. And our experience over the years has been that they can be unpredictable at the times when you don't want them to. You're using a lot of bandwidth at this moment, and it turns out the SSD decides it needs to garbage collect, and all your transactions slow down. So these unexpected behaviors make it really hard to deliver consistent performance and to run certain workloads. So how can we get the performance consistency we needed here? This is a rendering of a Graviton3 storage server, and the devices you see in the back there are the NAND chips. Of course, you probably know where I'm going here. We took one of our Nitro chips and added it to the device, and we run the flash translation layer on this Nitro chip. And the results there have been pretty outstanding. We've announced 3 different instance types based on these Nitro SSDs: the i4i, the im4GN, and the is4GEN. They have up to 60% lower average I/O latency, up to 75% lower tail latencies than our previous generation of i3 instances. These improvements let us run latency-sensitive workloads better. One customer who's been experimenting with these systems is Splunk. Splunk's a leading data platform provider, and when they looked at an im4GN with the Nitro SSDs, they observed up to a 50% decrease in search runtime compared to their i3 and i3N instances, and are eager to adopt them. So we've taken that server, and we've moved a lot of the I/O functionality off of that host CPU and onto these special purpose Nitro cards. DOM0, that privileged domain in Zen terminology, is significantly offloaded with a bunch of its functionality moved away. And now after offloading all that I/O to dedicated hardware, you can go back and revisit what the hypervisor needs to do. And this led us to a lightweight hypervisor with all the previous functions we discussed removed, which really does just 2 things: memory allocation and CPU allocation. This lightweight design reduces its size and enables bare metal-like performance. Then we added the Nitro security chip. This is a device we've put on all our motherboards that provides a simple hardware-based root of trust. It lets us measure the contents of the flash devices on the motherboard so we can be sure we're running the firmware we expect, and then monitors the hardware interfaces that would attempt to modify them so it can block any unauthorized modification. So now we move the I/O functionality. We've also moved the management and monitoring functionality off to the Nitro cards. And we can remove this DOM0 and actually just replace Zen with a new Nitro hypervisor. So let's talk a little bit about what the performance implications of that have been. In this graph, I'm showing you the system response time, meaning how long does it take after a timer expires or a packet is received for the virtual machine to start running. And the x-axis is response time in microseconds. And on the y-axis, it's the probability of getting that response time. Every system has some variability, so it's not just one point. With the C4 instance, this was the last instance before you moved to the Nitro system. You can see that the response time varies from about 70 to maybe 170 microseconds. This is bimodal distribution. With the C5 instance, this changed a lot. 2 things happened. One, the distribution tightened, and then it also shifted way over to the left. If we look at one of our newer instances, a C6G, which is a Graviton-based instance, it tightened even more and shifted even further to the left. So there's a very significant improvement in response time with the Nitro system. Nitro also has enabled us to remove a lot of human interaction from our systems. We define computing as the use of specialized hardware and associated firmware to protect customer code and data from outside access. And we designed the Nitro system to ensure workload confidentiality not only between customers, but between customers and AWS. There's no mechanism for any system or person to log into these Nitro-based EC2 and servers, the underlying hardware, and access customer data. And there's no root user or interactive access, only a narrow set of authorized and authenticated APIs that don't have access to customer data. So we talked about performance and security, but there's one other aspect to the Nitro system that I want to share to you, and that's really the velocity and the pace of innovation we've been able to bring with Nitro. We have these modular building blocks now with lots of functionality on particular pieces of hardware. And so we can take one of these Nitro cards and we can put it in an AMD server or an Intel server or a Graviton server and get all that functionality across those 3 different platforms without spending significant resources trying to run those on a host CPU. Before Nitro, it took us 11 years to go from 1 instance to 70. And in the about 4 years or 5 years since we announced Nitro, we've gone from 70 to around 500. And these 500 provide lots of flexibility to choose the optimal instance type that you might need for whatever your specific use case is. Okay, so I'm going to change gears a little bit, and I'm going to talk about host compute. Graviton is a line of ARM-based processors that are available exclusively in AWS and provide the best performance and price performance in their instance families. We announced the original Graviton back in 2018. And really what we did was we proved that we could have an ARM-based instance in EC2, and you could interact with it like you'd expect. You could run different AMIs, you could attach and detach ENIs and EBS volumes, you had elasticity, wide OS support. But it wasn't until 2019 that we really started changing the game a little bit and found a lot of excitement here. In 2019, we announced Graviton3. Graviton3 was a very different chip. It has 6 times the number of transistors from the original Graviton, around 30 billion, 4 times the number of cores, around 2 times the performance per core. And we went from, honestly, a curiosity to the best performance and price performance in EC2. 2 more years later, last year at reInvent, we announced Graviton3. Again, almost doubling the number of transistors that we had to 55 billion, and another huge step up in perf. I'm going to talk a bit about Graviton2, and then I'm going to talk about the changes we made in Graviton3. So today, with Graviton2, we have 12 different instance types that are powered by it across 23 different AWS regions worldwide. This includes general purpose instances like the M6G and M6GD, burstable instances with T4G, compute-intensive ones with C6G or C6GD, and also a C6GN, a high networking instance, which is one of the best places to run network appliances. R6GD, R6G, and X2GD are for memory-intensive workloads with up to 16 gigabytes of RAM for every vCPU in the system. And in the last few months, we've released IM4GN and IS4GN. These are storage-focused instances that use those Nitro SSDs I talked about a little while ago. And also a G5G, which is a GPU-based instance for graphics, machine learning, and gaming workloads. One of the simplest ways to consume Graviton is through our managed services. We support 6 different databases of our managed services, including DocumentDB and Aurora, Amazon RDS and Elasticache, both of which use Graviton as the default if you don't specify an instance type, Amazon MemoryDB, which is exclusively run on Graviton, and Amazon Neptune. On the analytics space, we have support for OpenSearch and EMR, and we've heard from customers that they could just change a CloudFormation template with 10 characters, and not only did they get higher performance, they were also saving money. In the last year, we've also seen our compute services like Lambda, Fargate, and Beanstalk adopt Graviton and provide that as an option. And we've seen customers from large enterprises to startups across different verticals and segments and geographies adopt Graviton-based EC2 instances, as well as managed services. Typically, customers start by migrating a single workload, find that it was easier than they thought it was going to be to migrate, and then start moving more. And I usually recommend that you find a workload that has modern dependencies. You don't want to be dragging some code from 15 years ago, and the one that you know how to measure the performance of, so you can actually quantify, did you see a performance improvement? Did you see a cost improvement? For example, DirectDV started with 1 microservice in July 2021, and by the end of 2021, they had migrated over 100 microservices. We have customers like Discovery, who use Graviton-based EC2 instances to reach 175 million viewers during the Tokyo Olympics. Epic, which is known for the Unreal Engine, and Fortnite, who run Fortnite servers on Graviton. Lyft, which uses a combination of Python and Go and found 30% better price performance by adopting Graviton. And Snap, who uses EKS on Graviton to run their messaging core service. Okay, so we talked about Graviton2. Now let's spend a little bit of time on Graviton3. This is the Graviton3 chip. And the first thing that might pop out at you is it's actually composed of 7 different chiplets. There's 1 main compute die and some I/O dies around it. I'll talk more about that in a little bit. It's 55 billion transistors, almost twice as big as Graviton2. And the most impressive part of it is that in one generation, we've added over 25% performance. Typically, when you go from generation to generation, we're kind of used to 10%, or maybe if it's a good day, 15% performance. Here we've added 25 in one generation in 2 years. And this is a system that has the first DDR5 system in our data centers, providing you up to 50% more bandwidth. So let's dive into some of these innovations in Graviton3. Graviton3 runs at a slightly faster clock, but it really gets most of its performance by executing more instructions per cycle, or IPC. Going from that 30 billion to 55 billion transistors, I can tell you where most of them went. They went into every core that you see here. We made the cores bigger. There's a 2x wider front end, a much bigger branch predictor that predicts branches better for larger workloads, and a 2x larger instruction window. We doubled the width of the SIMD units. So for media encoding workloads, we see huge performance increases. We also added support for bfloat16 for CPU-based machine learning workloads, SVE for HPC workloads. To feed all of this, we doubled the number of memory operations that can occur per cycle, added enhanced prefetching, and doubled the number of memory operations that every CPU can make to the rest of the system. We have twice the ALUs, which is really important for RSA TLS session negotiation performance. And we added some security features, like pointer authentication, which is a way to prevent return-oriented programming attacks, and a very fast, user-accessible random number generator instruction. One of the biggest differences between Graviton and our x86 instances is what a vCPU means. On our x86 instances, a vCPU is sharing some processor execution resources. And this is good if the CPUs aren't very busy. You get higher efficiency by sharing those resources. But if they are very busy, now you've got contention, both in the processor core and also the shared L1 and L2 caches. With Graviton, every vCPU has its own set of resources. The vCPUs can't interfere with each other, they don't affect the performance of each other, and there's a stronger security boundary there. One of the things that customers loved about Graviton2 was there was no NUMA domains. NUMA stands for non-uniform memory architecture. It really says, is the path from a CPU to memory the same, or is it widely different? And if it's widely different, then you have to start worrying about where am I going to put my memory versus my compute. Most people just rely on the operating system to hopefully guess for them, but it has really imperfect information. So we wanted to build a big chip, but we also didn't want to add NUMA complexity to it. So we started with this big die, and we put 64 cores on it. We connected it together with a mesh that runs at 2 gigahertz and has a bisection bandwidth of over 2 terabytes a second, and then distributed a last level cache throughout that mesh, so you can have really high bandwidth access to it. After that, then we added these dies on the side that are our DDR5 channels. We have over 300 gigabytes a second of theoretical memory bandwidth, and this is really easily accessible memory bandwidth. If you run simple loops on all the cores, you'll get it all. No special instructions or hand-tuned loops. Just simple for loops on all the cores will get it for you. And just like Graviton2, we have always AES-256 encrypted DRAM with an ephemeral key. Those last two devices you see on the bottom, those are our PCIe chips. Now the innovation with Graviton didn't stop just with the chips. We also got to look holistically at the server and even the racks that we were putting them in. So in a data center, you typically end up having racks, and the racks have a certain amount of space and a certain amount of power. Ideally, you want to balance this. You'd like to use all the space in the rack, and you'd like to consume all the power in that rack position. But with a lot of systems in our data center, we can't do that. We typically use all the power before we fill up all the space. Except Graviton here is different. We typically run out of space in the rack before we run out of power in the rack position. So what can we do with Graviton3? A standard server has 2 sockets, and if it's an AWS server, it's going to have one of these Nitro cards. But why is 2 a hard and fast rule? When we started this, we knew we wanted to increase the density in every server, and we wanted to try to squeeze more sockets in there. So we built the chip the package, and the motherboard to fit not 2, but 3. So every Graviton server has 3 Graviton chips. This increases the sockets per server by 50%, can increase the sockets per rack by 50%. It comes closer to the power requirements of some of the other solutions we have. And that Nitro Card can manage those 3 sockets simultaneously. So how does it perform? I don't have time to talk about all the benchmarks that we've looked at, but I'm going to share one workload. Obviously, it depends on the workload you're running, and some customer quotes, what customers have told us about running on Graviton3. So here I'm running Node.JS, a Node.JS app called Acme Air. It's a little sample app that does flight scheduling. We've got 1 copy running on every vCPU, and we're running it on a Graviton2 based C6G or a Graviton3 based C7G. And keeping everything else the same. Same load generator, same database, just flipping out the instances. And you can see in this one generation, we've got 37% more performance from this one application. Now, it's not just our numbers. Twitter looked at Graviton3 based C7G's instances and found for workloads that are representative of what they do in production, they found between 20 and 80% higher performance versus Graviton2, and a reduction in tail latencies by as much as 35%. Honeycomb was one of the first companies to adopt Graviton2 in production. At this point, they've moved all of their x86 compute to Graviton. They do not have any more x86 servers running in production. And they looked at our Graviton3 systems, and because of the increased performance, they could reduce their fleet size by 30%, and also saw a 30% reduction in latency. Epic, who I talked about before, says that the C7Gs are suitable for even the most demanding latency-sensitive workloads while providing significant price performance benefits. And lastly, F1 does computational fluid dynamic simulations. They want to look at the airflow over cars to understand how close another car could follow and how much downforce these cars would generate. And a C7G provided 40% more performance than a Graviton2 based C6GN. So with Graviton, we've got industry-leading performance with the CPU. We've got amazing efficiency, using up to 60% less power for the same performance than comparable EC2 instances. The first system in EC2 with DDR5. And this, combined with the silicon innovations, the multi-chip design, the reduction in costs and increased density in the racks, mean that we have the best price performance in EC2. So we've covered data center infrastructure with Nitro. We've covered host compute with Graviton. Now let's focus a bit on machine learning with Inferentia and with Trainium. Machine learning has 2 phases. First, you train a model, and then you use that model to do some inference. You can think of these models as really large parameterized functions. In the training phase, you're feeding the system with a set of examples that you know the answer to these parameters, so it can learn how to do a certain task. And the inference phase, you're not going to modify the parameters anymore, but you're feeding in unknown data and expecting to predict what the right answer is. These 2 have very different needs in terms of memory bandwidth, in terms of amount of computation, in terms of the scale, and the network bandwidth. In 2019, we announced the Inferentia chip as the lowest cost machine learning inference in EC2 with up to 80% lower costs versus GPUs. And last year at reInvent, we announced Trainium, optimized for training, the lowest cost training, and it'll be GA soon. Connecting both of these are the AWS Neuron SDK, which allows users easy deployments to either type of inferentia or training and to use the machine learning frameworks that they use today, like PyTorch and TensorFlow. Let's take a close look at inferentia first. So the Inf1 server is powered by 16 inferentia devices. Each one of those devices has 4 neuron cores and a 2-stage memory hierarchy and can produce up to 128 teraops a second. Each large on-chip cache allows the neuron cores to get terabytes a second of memory bandwidth out of. And then there's some commodity DRAM that's shared across those neuron cores. We also implemented an interconnect technology, which allows us to combine the neuron cores together in the chip and outside the chip into a larger virtual device where we can pull more data out of the caches instead of DRAM and meet lower SLA targets for inference. As I mentioned, we support popular ML frameworks and data types, so you can deploy to inferentiate easily without doing model tweaking, without doing data type conversion or quantization. Just bring the model as is and run it and get good performance. Inferentiate instances come in a range of sizes, from a single chip in the XL size up to the 16 chips in that 24 XL size. And probably most importantly, the Inf1 instances allow you to use them as direct EC2 instances through services like SageMaker or through our container runtimes like ECS and EKS. And we've seen a lot of customers realize the benefits of the inferentiate devices. Customers like Airbnb, Autodesk, Snap, and Sprinkler are all using Inf1 on a variety of models, from natural language processing, computer vision, recommendation engines, and they all report significant price and performance improvements. Let's dive into a couple of those. Airbnb has a community support platform that's used by millions of people every day. When a customer accesses information, Airbnb wants to give that to them as fast as possible. And so they switched to an Inf1 instance for a natural language processing chatbot they had, and saw a 2x higher throughput for this PyTorch-based BERT model. Similarly, Amazon Prime Video has live event streaming, where they use machine learning models to analyze the video quality of live events and to ensure an optimal viewer experience. They deployed these image classification models on the Inf1 instances and saw a 4x improvement in performance, and that also led to up to a 40% savings in cost. Let's take a closer look at the cost savings. In this graph, I'm showing the cost per inference, so lower is better here. I've added not only the G4 but also the G5 instance, and we've got 3 different machine learning models. YOLO v4, which is an object detection framework with TensorFlow. We have an NLP workload with BERT and PyTorch. And lastly, ResNet50, which is an image recognition model. It's often used for benchmarking. And across all these, we see numbers like 2x lower cost per inference, or even 4x lower cost per inference for the language models. Just really large numbers. By specializing inferentia for inference workloads in particular, we're able to cut down costs and improve power efficiency. Here we're taking that same YOLO v4 network that we saw on the previous slide and feeding many images through it. And there's a distribution in performance per watt just based on the complexity of the various images. But between them, on the high end, inferentia is about 3x higher performance. On the other end, it's 1.6x higher performance, but the median's around 2. So that means inferentia instances are greener, they're cheaper to operate, and we get to pass those savings onto you in the instance price. So we've talked about inferentia. Now let's spend a few minutes talking about training and with Trainium. Most training is a scale-out task. And so we want to innovate not only at the chip level, but also the system level to be able to train larger models. Trainium has 60% more memory per device than our P4Ds. We've also added twice the network bandwidth, with up to 800 gigabits a second of networking. Both these drive better time to train and the lower cost to train and higher performance efficiency. It leverages that same Neuron SDK with integrations into PyTorch and TensorFlow, so you can get started quickly and easily. And just like Inf1, it'll be available with AWS services like SageMaker or container runtimes like ECS and EKS. And Trainium allows users to have 2 different instance sizes. One, a 2x large for small models or for just getting started. And the other, the 32x large, to have all 16 devices that are in an inferential system and scale out from there to tens or even hundreds of nodes. Our customers use different data types. So in order to optimize for training accuracy and speed, TRN1 is the fastest instance we have across a variety of data types, including bfloat16, or 1.4x faster than a P4, TF32, or 3.5x faster, and FP32, or about 5x faster. TRN1 also introduced a new data type called the configurable float 8. This has a set of advantages. Because of its smaller size, it means the model footprint's smaller. It means you need less I/O to train. And with configurable float 8, you can trade off between range and precision, even on a per operator basis. So as I mentioned, TRN1 was built for massive scale-out training. So it has a 60% increase in accelerator memory footprint, but also the highest amount of network bandwidth and inter-chip bandwidth of any of our training-focused instances to date. So now we've covered machine learning, data center I/O, and host compute. And we're just starting the journey here. We've done a number of devices, but we're going to keep iterating. We're going to make them better. We're going to make them higher performance. We're going to keep raising the bar in security, keep innovating across the boundaries, and providing you the best performance and price performance that we can. So thank you. I'm sure you've seen this slide more times than you probably want, but if you would like some training opportunities, you can look at Skill Builder or the AWS certifications on the right there. Thanks a lot.